Okay, so here, just a quick video key for the quiz 2. So first of all, you might have noticed the second question on quiz 2 was identical to one of the questions on quiz 1. So if you're interested in that resonance structure, go to the quiz 1 key. The lesson there, and I say this in the printed key, is that you should not just be taking these quizzes and tests and then forget about it. They're not just for points. You should use them to learn. So if you take a quiz and you don't know what the answer is, go and look at the key, study up on it. Even if you think you know what the answer is, go look at the key and make sure you understand it. So you will, from time to time, see problems again in this class, and you should be ready for that. So quiz 2 key, all I'm going to do is number 1. I ask you to draw the most stable Newman projection for 3-bromo-2,2-dimethylpentane, and I specify that you're looking down the C3-C4 bond. Okay? I think a few people were confused by this. When I say looking down, I mean that that's the bond that we're using as the basis for the Newman projection. So either the C3 carbon is in front and the C4 carbon is in back, or the C4 carbon is in front and the C3 carbon is back. Those have to be the two carbons that we use to base the Newman projection. So first things first, let's get the name, let's get the molecule for 3-bromo-2,2-dimethylpentane. So pentane, 1, 2, 3, 4, 5. Okay, 2,2-dimethyl, so let's just, we can start wherever we want this time. So 1, 2, so there's 2 methyls there. 3-bromo, 1, 2, 3, so the bromide is there. So there's the line structure for 3-bromo-2,2-dimethylpentane. And now if you go in and do numbers, 1, 2, 3, 4, 5. Okay, so the bond I want you to draw the Newman projection around is the C3-C4 bond. So that means either carbon 3 is in front or carbon 4 is in front. Right? And so we can either look this way or we can look this way. I'm going to work this a couple of different ways. First, I'm going to do this from, right, as if I'm looking right here, so I'm looking there. So the C3 carbon will be in front. Okay, so I'm looking here. Got a T-butyl group up. And now where's the bromide? Well, drawn this way, that's just a line, and it suggests that it's in the plane of the board. But you've got to know, go back to fundamentals. What's the hybridization of carbon 3? Right? It's sp3. So carbon 4 is sp3 as well. That tells you that carbon 3, if it's sp3, has bond angles of 109.5. It's tetrahedral. So this bromine is not really like that. It's either going back or it's coming out. Let's say it's going back. That means a hydrogen is coming out. Okay, so if I'm down here like this, that puts a bromine down to the left and H down to the right. C4, if I'm looking down here, C5 then is down. Again, it's tetrahedral. I've asked for the most stable conformation. It's going to have to be a staggered conformation. The two things coming off C4, one out at us, one back away from us, are hydrogens. So you fill those in. All right. You could have chosen to put the bromine on the wedged bond and the H on the other bond, in which case this bromine would be there. And you'd get a relationship. The structure you'd get there would be the enantiomer of the structure you get here. All right, so as I shoot this video, we haven't talked about enantiomers in class yet. We will in a bit. The way I drew this originally, though, you could choose either enantiomer. You could put the bromine on either side and it would be fine. And that's actually it. Most stable conformation. Well, you've got the big group on the front carbon. So this front carbon, C3, T-butyl, is a lot bigger than bromine. Big group on the back carbon is methyl. And the big group on the front and the back are anti to one another. And you've pretty much minimized gauge interactions. You've got a methyl gouged with the bromine. The only way, well, you can't actually, if you're going to have the T-butyl group be anti to the methyl, the bromine's got to be gouged to the methyl. There's really nothing you can do with that. That's the most stable conformation. So let's look at it if you do C4 in front. So that is, no, we're not going to look the other way. All right, C4 in front. If I'm looking there, methyl is down. H is up. And as I look here, I'll come around, right? I'm peering down this way. Got an H coming out, a bromine going back. So that's an H to the left, a bromine back, and then the T-butyl group is sticking up off that back carbon. All right, so that's with C4 in front. And if you look at this, if I take this Newman projection and I turn it over and I lay it there, they exactly overlay. The back carbon comes to the front carbon goes to the back. It doesn't matter what direction you look at the molecule from. The conformation is the same. It's got to be staggered. You want the big groups anti, and you want to minimize the Gauss interactions. All right, so bookkeeping, some of you are going to have drawn, some of you will have gotten the molecule wrong. So you'll have screwed up the nomenclature. All right, that'll be a minor deduction, but if you do everything else right from there, you'll be all right. Some of you will have looked down the wrong bond. Again, that's going to be a minor deduction. I've seen a lot already where people are looking down the C2, C3 bond. I don't really understand why you did that, but it could be a nomenclature thing as well. But again, if you did it okay, except for that one thing, it'll be a minor deduction. All righty.